In the previous video, we introduced how to think about probability in terms of sets. We talked of a sample space, which is the set of all possible outcomes. Outcomes, which by definition are mutually exclusive. These are outcomes of a random experiment. Events, which could overlap. They're not mutually exclusive. And we treat these events as subsets of a sample space. And anyway, we defined a probability measure with some axioms, and we said you can derive some theorems from those axioms so that the probability measure maps from events in your sample space to the real line between 0 and 1. So that's the beginnings of probability. Now we'll define conditional probability. Here's the notation for it. And what does that mean? The probability of getting an outcome that is in the subset B, given that you know that outcome is in the subset A. If this were like drawn to scale, where areas matched probabilities or how many outcomes, the probability of A would be the area of this circle divided by the area of the whole space. And the probability of B would be the area of B divided by the area of the rectangle, the whole space. And the probability of the intersection A would be this, the area of this little overlapping region divided by the area of the whole rectangle. But if you know it's in A, everything outside of A can't be an outcome. So you know this, it's like A becomes your new subset. So that this probability is the area of this overlap divided by the area of the A circle. Given that this probability of A is not 0, otherwise you'd have divide by 0. But this is a definition anyway, just trying to make it make intuitive sense. And you'd have the same type of thing. What's the probability of getting an outcome in A, given that you know it's in B? And there it is by definition. We didn't really derive anything here, we defined it. But from those two things, from just the definitions of conditional probability, you do a little very basic arithmetic, you get this pretty fundamental theorem of Bayes' theorem, which says how to write this conditional probability in terms of its sort of inverse conditional probability. And we'll get to an example of this when we maybe clear it up. So you have this, well, let's go over here. The probability of A given you know it's in B. The probability of B could be written this way. If you have a bunch of events that are mutually exclusive, so their intersections are the null set, that means they don't overlap at all. And the union of all those events is your whole sample space. Okay? So the A's, the event A's are all the event, they fill up your sample space and there's no overlap between them. Then the probability of this B is just the sum. Probability of B given each one of those times the probability of that event, sum it over all those events. We'll come back to this as kind of a formula. Let's do an example. Say there's a certain disease which has a prevalence of 1 person in 1,000 has this disease. That's all we know before we do any new testing. Somehow we know that's the prevalence of the disease. The test has a success rate of 99%, meaning of every 100 persons who have the disease, the test will give a positive result 99 times. Has a false positive rate of 1%, meaning of every 100 persons without the disease, get a positive test one time out of 100. That's what the 1% is. Okay, what's the probability you have the disease given you test positive? Well, we go back to our Bayes theorem. Here, that sum on the bottom, there's just two possible outcomes. I'll say D means you have the disease, and T means you test positive. So this probability that's in the denominator, remember that sum? The D is either you have the disease or you don't have the disease. Those are mutually exclusive and they cover all possibilities. Then you map these words to what all these terms are. The probability that you test positive given you have the disease is that success rate of 99%. The probability that you test positive given you don't have the disease is that false positive rate of 1%. Probability that you have the disease before you do a test, 1 in 1,000. Probability you don't have the disease. Remember, this was a result of how probabilities work. Probability of the complement of a set is 1 minus the probability of that set. That's 999 out of 1,000. Put all that together in your formula, you get 9.02%. So you don't even have a 10% chance that you really have the disease, even though you tested positive for it, and they call the success rate is 99%. If you just looked at these numbers, you probably wouldn't come up with this. In fact, when they give this type of problem to doctors, they majority of the time, they don't get it right. They're wildly off. They'll say it's like, oh, you got a 90% chance of having a disease. No, it's not even 10%. One more little thing before we get off into the next subject, which is going to be random variables, is the definition of independence. And here's what it means, and it's a definition. You say A and B are independent. A and B so far are subsets of our sample space. They are independent if their intersect, the probability of their intersection is just the product of their individual probabilities. Kind of a consequence of that, this conditional probability, if they're independent, then the probability of A given you know it's in B is just the probability of A. The probability of B given you know it's in A is just the probability. That's kind of like if you go back to this. It'll make sense to me someday. Okay, we'll get into random variables next time. Video. Slowly getting a better handle on this. From sets and subsets to numbers.